In this video, we're going to focus on double integrals. So how can we evaluate the iterated integral that we see on the board here? Before we begin, the first thing you need to realize is that the numbers 1 and 3 correspond to y. Those are y values. And notice that dx is written later. Therefore, 0 and 2 are x values. So just keep that in mind. What we're going to do is we're going to work from the inside towards the outside. So we're going to evaluate this integral in the middle. So let's do that over here. So we have the integral from 1 to 3 x y squared dy. So dy tells us that we're integrating with respect to y, which means that we're going to treat x as if it's a constant. So what is the antiderivative of y squared? The antiderivative of y squared is going to be y to the third divided by 3. You need to add 1 to the exponent and then divide by the result you get. So now we're going to evaluate it. But since we have two variables, an x and a y, we're going to specify that we're replacing y with 1 and y with 3. So this is going to be x over 3, and then we're going to replace y to the third with 3. So it's going to be 3 to the third minus 1 to the third. 3 to the third power is 27. 1 to the third is 1. So this gives us 26 over 3 times x. So we're going to replace what we have in the brackets with what we see here. So right now we have the integral from 0 to 2 of 26 over 3x dx. So now let's find the antiderivative of x to the first power. So we're going to add 1 to the exponent, it's going to become 2, and then divide by that result. Now, we're going to plug in 0 and 2. We don't need to write x equals 0 and x equals 2 because we only have one variable in that expression. 26 divided by 2 is 13. So we have 13 over 3 times x squared, and we're going to evaluate it from 0 to 2. So let's take out the constant, and let's replace x with 2, so that's going to become 2 squared, and then once we replace it with 0, we have that. 2 squared is 4, and 13 times 4 is 52. So the final answer for this problem is 52 over 3. In the last problem, we saw that the value of this double integral was equal to 52 over 3. But what's going to happen if we change the order of integration? Let's say if we put the 1 to 3 first, what's going to happen? It turns out that the value of these two integrals are the same. Now keep in mind, the numbers 1 and 3 correspond to y. So if you put the integral with the 1 and 3 on the outside part of this expression, dy has to be on the outside part as well. So that's just one thing to keep track of. So let's start with the integral on the inside. So we're integrating with respect to x. So y squared is going to be the constant here. So this is going to be y squared times the antiderivative of x to the first power, which is x squared over 2. And we're going to evaluate it from 0 to 2. So this is going to be y squared over 2, and then x squared, that's going to be 2 squared minus 0 squared. So 2 squared is 4. 4 divided by 2 is 2. So right now we have 2y squared. So let's replace this expression with 2y squared. So this is going to be the integral from 1 to 3 of 2y squared times dy. The antiderivative of y squared is y to the third divided by 3. And now let's evaluate it from 1 to 3. So let's take out the constant, which is 2 over 3, and then let's replace y with 3, and then replace it with 1. So 3 to the third is 27, 1 to the third is 1, so this is going to be the same thing. 27 minus 1 is 26, and 2 times 26 is 52. So this gives us the same answer of 52 over 3. So if you reverse the order of integration, the answer is going to be the same. But when you do it, you need to make sure that the y values correspond to what they should correspond to. So just be careful with that. So in this case, x corresponds to 0 and 2, and y corresponds to 1 and 3. Here's another problem that you could try. Go ahead and evaluate the double integral shown above using the information on the upper right. So we have the rectangular region R, and we have the values for x and y. So we can represent the iterated integral two ways. We could start by writing the x values first. So this would be an integral from 0 to 1, and then another integral from 0 to 2 of the expression 2y minus 3x squared y squared. Now we can replace dA with dx and dy. Now 0, 2 corresponds to y, so we need to write dy first, and then dx. Or we could represent it this way. We could write the y values before the x values. And then this would be times dx and then dy. So it really doesn't matter which way we choose to solve it. So I'm going to focus on this particular integral. So let's evaluate the integral from 0 to 1 of 2y minus 3x squared y squared dx. So that's going to be with respect to x. 2y is a constant. The integral of 2y dx is just going to be 2y times x. And then we have minus 3y squared. The antiderivative of x squared is going to be x cubed over 3, evaluated between 0 and 1. So here we can cancel out a 3. So this is going to be 2y times 1 minus y squared times 1 to the third, and then we need to plug in 0. So it's going to be 2y times 0 minus y squared times 0 to the third. So all of this ends up being 2y minus y squared. So we can replace this portion with 2y minus y squared, thus giving us the expression, the integral from 0 to 2 of 2y minus y squared dy. So the antiderivative of y to the first power is going to be y squared over 2, and for y squared it's going to be y to the third over 3, evaluated from 0 to 2. So if we plug in 2 first, it's going to be 2 squared, and then minus 2 to the third over 3. And then once we plug in 0, this entire expression will be 0. I mean this expression. So this gives us 4 minus 8 over 3. 4 is 12 over 3. 12 over 3 minus 8 over 3 is 4 over 3. And so this right here is the answer for this problem. Now let's move on to our next problem. Go ahead and calculate the value of this integral. So let's start with this expression, the integral from 0 to 2y of 4 plus 2x minus y squared dx. So we're going to integrate with respect to x first. The antiderivative of 4 is going to be 4x, and for x it's x squared over 2. Y squared will be treated as a constant, so we're just going to add an x to that. And now we're going to evaluate it. Keep in mind these are x values from x equals 0 to x equals 2y. So everywhere we see an x variable, let's replace it first with 2y. So this is going to be 4 times 2y, and then we could cancel 2, so that's x squared, but this is going to become 2y squared, and then minus y squared. Replace x with 2y. And then once we plug in 0, every term here will equal 0. So I'm just going to put 0 inside this bracket. So we're going to get 8y plus 2y squared is 4y squared. And then y squared times 2y, that's 2y to the third. So that's the expression that we currently have. So at this point, this is equal to the integral from 0 to 1 of 8y plus 4y squared minus 2y cubed, and then dy. The antiderivative of y to the first is y to the second power over 2. And for y squared, that's going to be y to the third over 3. And for y to the third, it's y to the fourth over 4, evaluated from 0 to 1. Now let's simplify what we have. 8 divided by 4 is 2. And then we have 4 over 3 y to the third. And 2 over 4 can be reduced to 1 over 2. So now let's plug in 1. So it's going to be 4 times 1 squared, which is just 4. And then plus 4 over 3 minus 1 over 2. When we plug in 0, this entire expression will equal 0. Now, in order to perform the operation here, we need to get common denominators. So let's get a common denominator of 6. I'm going to multiply 4 by 6 over 6, which will give me 24 over 6. 4 over 3, I'm going to multiply that by 2 over 2, which will give me 8 over 6. And 1/2, I'm going to multiply that by 3 over 3, which is 3 over 6. Now, 8 minus 3 is 5. And 24 plus 5 is 29. So this is the answer for this problem. It's 29 over 6. Now here's another type of problem that you may need to know how to do. So what do you think we need to do for this particular double integral? Go ahead and pause the video if you think you might know what to do. So here we have our rectangular region defined by these values. What you need to know is that this is A, that's B, this is C, and this is D. So the first thing that are written are the x values, and C and D represent the y values. So we can write our integral this way. I'm going to start with the y values first. So we have the integral from 0 to 3, and then another integral from 0 to 2 of the expression 4x plus y raised to the third power. Now, because we have the y values, the x values here, we need to put dx first and then dy. So keep that in mind. So now go ahead and finish this problem. Feel free to pause the video and work on it yourself, and then play it once you have the answer. So let's begin with the integral on the inside. That is the integral from 0 to 2 of 4x plus y raised to the third power times dx. Now let's use U-substitution for this problem. So we're going to say that u is equal to 4x plus y. Now, we need to differentiate with respect to x. So du is going to be the derivative of y. We're going to treat this as a constant, so that's going to disappear. The derivative of 4x will be 4 times 1 times dx. And so solving for dx is going to be du divided by 4. So now we're going to have the integral of u to the third power, and then replace in dx with du over 4. And so this is what we now have. Now we need to replace the values that we see here. And so those are x values. So if we plug in x equals 0 into that expression, it will be 4 times 0 plus y. So that becomes simply y. Now, if we plug in 2 into this expression, it's 4 times 2 plus y, which becomes 8 plus y. So now we could take the antiderivative of u to the third. So it's going to be u to the fourth over 4. The du is gone, but we still have this other 4 on the bottom. So that's times 1 over 4, evaluated from y to 8 plus y. So now we could plug these numbers in, and 4 times 4 is 16. So we're going to have 1 over 16, and then it's going to be 8 plus y raised to the fourth power, and then plug in y now. That's just going to be minus y to the fourth. So this is the answer that we have currently. So we could say that the original integral is now equal to the integral from 0 to 3 of 1 over 16 times 8 plus y raised to the fourth power minus y to the fourth, and then dy. So now let's rewrite the constant in the front. The antiderivative of 8 plus y raised to the fourth power is going to be 8 plus y raised to the fifth power divided by 5. And the derivative of y is just 1, so we really don't need to use U-substitution. If you did use it again, you should get that. If you made u equal to 8 plus y, du would just be equal to dy. The antiderivative of y to the fourth is y to the fifth over 5. And so we're going to evaluate this from 0 to 3. Plugging in 3, we're going to have 1 over 16 times, this is going to be 8 plus 3, so that's 11 to the fifth power over 5. And then minus 3 to the fifth power over 5. Now we need to plug in 0. So it's going to be minus 0 plus 8, that's just going to be 8 to the fifth power over 5. And then 0 to the fifth power is just 0. So this is going to be 11 to the fifth power minus 3 to the fifth power, and then minus 8 to the fifth power. And these are all divided by 5 since they share the same denominator. And there's a 16 in the bottom, so I'm going to put 16 times 5. Now, 11 to the fifth power, that's 161,051. 3 to the fifth power is 243. And then 8 to the fifth power, that's 32,768. And 16 times 5 is 80. So 161,051 minus 243 minus 32,768, that's equal to 128,040. And we're going to divide this by 80. So for starters, we can cancel a 0. So now we have 12,804 divided by 8. If you divide it by 2 again, 12 becomes 6, 8 becomes 4. So you get 6402 divided by 4. And then you can divide that by 2 again. Half of 64 is 32. Half of 2 is 1. So you get 3201 over 2. So this right here is the final answer. Here's a challenge problem for you. Go ahead and work on this problem. Now, in order to evaluate that iterated integral, we need to use U-substitution. So we need to make u equal to x squared times y. But here's a question for you. Should we differentiate u with respect to x or with respect to y? Now, looking at this problem, we may have to differentiate it with respect to y, but we can always reverse it. We can change the order of integration. So is it easier for us to evaluate this integral by integrating with respect to y first or with respect to x first? Well, let's find du. If we find du with respect to y, it's going to be x squared times the derivative of y, which is 1, times dy. Now, if we isolate dy by dividing both sides by x squared, we're going to get this. And so if we replace x squared y with u, and then dy with du over x squared, notice that we won't have an expression with the u variable only. We'll have a y eu over x du. And so this is not going to work out very well. So instead, what we want to do is differentiate with respect to x. Notice what will happen. The derivative of x squared is 2x, and then we're going to have dx. Y is a constant, so it comes along. So du over 2xy is equal to dx. And so xy will be canceled with part of the 2xy in the denominator. So that's going to work. But right now, we have dy written first. So we need to change the order of integration. So this is going to be the integral from 0 to 2, and then the integral from 0 to 3, xy e x squared y, and then we're going to put dx first and then dy. So let's focus on this part of the problem. So we now have the integral of xy and then e to the u. Now we're going to replace dx with what we have here. That's du over 2xy. And so we can cross out xy, and we need to change those values. So when x is 0, what is y? If we plug in 0 into that expression, we have 0 squared times y, that's just 0. Now when x is 3, what is u? I said y, but I meant u. So if we replace x with 3 in that expression, it's going to be 3 squared times y. So that's 9y. The antiderivative of e to the u is just e to the u. And we have a 2 in the bottom, so that's 1/2 e to the u, evaluated from 0 to 9y. And so this becomes 1/2, and then it's e to the 9y minus e to the 0. E to the 0 is 1, so we have 1/2 e to the 9y minus 1. So now we can replace what's in blue with that expression. So now we have the integral of, or from 0 to 2, of 1/2 e to the 9y minus 1, and then dy. So let's move the 1/2 to the front. The antiderivative of e to the 9y is going to be e to the 9y divided by 9. And the antiderivative of -1 is going to be -y. And so this is evaluated from 0 to 2. So those are the limits of integration. So let's begin by replacing y with 2. So it's going to be e to the 18, because we have 9 times 2, over 9 minus 2, and then minus, replacing y with 0, e to the 0 is 1, so over 9, and then minus 0. So this is, let's see, we have e to the 18 over 18, since that's 2 times 9, and then 1/2 times -2, that's going to be minus 1, and then this is 1/2 times 1 over 9, which is going to be minus 1 over 18. So let's see if we can put this all in a single fraction. So we have e to the 18 over 18. -1, we can write that as -18 over 18, and then minus 1 over 18. So -18 minus 1, that's -19. So I'm going to write it like this. This is 1 over 18 times e to the 18 minus 19. So this here is the final answer for this problem. So now you know how to work with double integrals, and you know how to evaluate it. I said that wrong. You know how to evaluate iterated integrals. So that's it for this video. Thanks again for watching, and don't forget to subscribe to this channel.